When a system receives heat, its temperature increases. The heat capacity of a system is the ratio between the heat and the temperature increase. For a pure substance, the molar heat capacity is the heat capacity per amount of matter. Molar heat capacity is widely used in science. From here, I will use a bar above a quantity to represent the molar quantity. The specific heat capacity is the heat capacity per unit mass. Specific heat capacity is usually used in industry. Heat capacity is a path function. It depends on the properties of the process. Molar heat capacity at constant volume is one of the typical heat capacities. According to the first law of thermodynamics, heat is the change of internal energy minus work. When the volume is a constant, the work is zero. So, the heat is equal to the change of internal energy. CV is the internal energy's partial derivative with respect to temperature with the volume held constant. Such notations of partial derivatives are frequently used in physical chemistry. So, you had better be familiar with them from now on. For example, the internal energy of a monatomic ideal gas is the kinetic energy of the translation of atoms, which is already calculated using the kinetic theory of gases. Thus, we can easily find the CV of monatomic ideal gases. This value is independent of the type of the gas. Molar heat capacity at constant pressure is another typical heat capacity. At constant pressure, PdV is equal to dPV. On one hand, the internal energy of an ideal gas is independent of its volume and pressure, but depends on a single variable, temperature. It is because there is no interaction between gas particles in the ideal gas. Thus, the internal energy's partial derivative with respect to temperature with the pressure held constant is equal to that with the volume held constant, that is CV. On the other hand, according to the ideal gas law, PV can be replaced by RT. Therefore, the difference between Cp and Cv is the ideal gas constant. The volumes of condensed matters do not change significantly with temperature. So, their Cp and Cv are almost identical. The Cp of monatomic ideal gas is 5/2 R. Here, I show you a list of Cp of a few gases. The Cp of monatomic gases is exactly the same as we calculated before. The Cp of diatomic gases at room temperature is higher than that of the monatomic gases by the value of R. It is because diatomic gases have 2 degrees of freedom in rotation. The rotational energy increases with temperature, which also contributes to the internal energy. In linear trimolecular molecules like carbon dioxide, the vibration also contributes significantly to the heat capacity at room temperature. So, it has higher heat capacity than diatomic molecules. In nonlinear molecules like ammonia and methane, there is 1 more degree of freedom in rotation. Thus, they also have higher heat capacities than diatomic molecules. Heat capacities depend on temperature. Here, I show you a plot of CV versus temperature of idealized diatomic gas. At low temperature, only transition contributes to the heat capacity. So, the heat capacity is the same as monatomic gases. As temperature exceeds critical temperature of rotation, rotation starts to contribute to the heat capacity. As temperature exceeds critical temperature of vibration, vibration contributes to the heat capacity as well. The detailed discussion on heat capacities from rotation and vibration requires high level of quantum mechanics and statistical mechanics. We will not discuss it in general chemistry. You can pause the video here to check the example question. We can use heat capacity to explain some natural phenomena. For example, the heat capacity of the sea is higher than that of the land. It is because liquids have more degrees of freedom of motion than solids. In the daytime, the land and sea receive same amount of heat per unit area from the sun. The land heats up faster than the sea due to its lower heat capacity. The hot air on the land elevates, leaving lower pressure on the land surface. Sea breeze brings moist air to the land, which then elevates and cools down to condense to water. So, there is a higher possibility of rain on the land. In the night, the sea cools down slower than the land. The hot moist air on the sea elevates and cools down to condense to water. So, there is a higher possibility of rain on the sea. The lower pressure on the sea surface brings land breeze from the land.